All right. First, yes, I'd like to thank God for allowing me to be here. Thank you for the invitation to speak here today. And also, I'd like to thank, and I hear from my collaborators who helped with understanding this. So today I want to talk about what is lack of microstructure and how to understand that maybe from a geometrical perspective. And Here's my outline. So I'll try to motivate why we should be concerned about this problem or these set of problems. What is black hole microstructure, microstates, and then I'll just briefly touch on a framework that we use called the fuzzball proposal. Then I'll sort of outline how we can use supergravity and to try to understand something called microstate geometries, which are geometrical configurations. And then I'll talk about the specific configurations that we've worked on, or some that I've worked on recently, and that have been worked on previously, called superstrata. This is just a certain class of geometry. Then I'll conclude, and if I have time, I'll conclude and do future directions. A lot of the talk will be here, and this is the first time I've talked about this particular aspect. So bear with me. I fear that maybe I have too many slides here, but we'll see. We'll see how it goes. So why should we be concerned about black hole microstructure? Well, what is a black hole? Sort of in simple terms, it's a region in space-time where light can escape, and it's defined by having a horizon that sort of tells you where this boundary is. It's a fictitious boundary. And then it's hiding a singularity. And since it has a size, since there's some horizon, there's some area associated with this, and called the Bekenstein-Hawking entropy. And sorry, the area, so then the entropy turns out to be related to the area, and it's called the Bekenstein-Hawking entropy. So this formula is really nice because what you see is all the fundamental constants. You see gravity, you see h bar, you see the speed of light, and you even see the Boltzmann constant. So maybe one way to think about the black hole is that it's a coarse-grained object. And you can understand it thermodynamically. There is, I even think Witten recently had some review of black hole thermodynamics. But there is this Boltzmann constant, and maybe you could ask the question the same way that we ask about maybe the molecules in the room. What are the microstates? What is the microscopic structure? What are the states that count this entropy? And that will be the sort of the motivation of this line of thinking. So black holes have an entropy, and Hawking also came along and showed us that if you apply quantum field theory in curved space-time, then black holes radiate. Sorry, wrong computer. But this, so if you take semi-classical gravity and quantum field theory, you can do that, and he did that, and found that what you find is that the horizon is sort of unstable for pair creation. But the thing is that when the pairs are created, one particle falls in, and the other one sort of escapes to infinity. And if they're entangled, this entanglement grows, and it's because of this boundary. And it seems like the black hole will shrink. And this is because the particle on the inside actually has a negative energy. And we can even sort of see this from a very naive calculation, quite remarkably, if I just consider a point particle in just a classical gravitational field. I have mc squared, and then I have the gravitational potential energy. There is a critical radius where this is 0, and if you're inside the radius, E is less than 0. Now this formula is only off by a factor of 2 from what GR will tell you. And so this sort of is a simple way maybe to see that the black hole on the inside will have particles will have negative energy. And so as this black hole evaporates, it looks like it's shrinking. It's shrinking. But then as it evaporates away, what is the conclusion? What happens to the information? And so because the entanglement continues to grow, and you can maybe think that there's correlations between the particles that are coming out, and that maybe somehow if these small correlations could add up to solve the problem, but there's these small corrections actually don't help, and maybe you need, yeah.
So all these are when the asymptotic space-time is flat.
That's right.
So
that's right.
the black hole in the box, large box, or in the ADS, let's say. Then how should we understand that quantum under the fault line statement, quantum vacuum unstable?
Maybe
is a thermal equilibrium.
Yeah, maybe in that case it'd be there's some type of equilibrium that you would have.
So does it mean that, of course, I mean the Hawking radiation is a local phenomenon, isn't that right?
It happens at the horizon, but sort of the particle only becomes, I don't know how you would say real once it's sufficiently far from the horizon. So an observer at infinity is going to see this this particle coming out, but this is entangled with the one that's falling, the one that fell in, and so this is sort of like this entanglement is growing, but this is happening at the horizon, but this is what an observer at infinity will see. Yeah.
Oh, sure. You can use this pointer.
Oh,
Do that one.
oh, great, thank you.
Also,
So,
point to them.
oh, okay. So if how, is there since as I was saying, these small corrections may not solve it. Maybe you want to put something there. Maybe can I put something there that sort of mimics the black hole? That's also really hard in the traditional sense, because there's something called Gauss theorem, and it says that if the radius of some shell is less than some critical value, then that matter should inevitably collapse. And there's some assumptions about perfect fluid, and the energy density shouldn't increase outward and things like that. But for the most part, it's really hard to put something at the horizon and keep it there, like traditionally. And so this leads into sort of this no-hair theorem, which says that the only thing that you can know about an object that made the black hole is its mass, charge, angular momentum.
So the wider factor is not 2n, but it should be a little bit larger than the horizon.
So I think so. This is the value that that I guess I went back on. It's kind of an old paper. So it doesn't mean that it's trapped. It just means that it's inevitably going to collapse down. It's hard to stay there. But the light cone hasn't. The light cone's not. So when you go across the horizon, the light cone sort of turns over, and you're never able to come out. But this just says that if it's below this region, it will inevitably collapse. But it's not the horizon. That's right. It's a little bit more. It's a little bit more than the horizon.
Yeah. So in other words, I don't understand why the bound is not horizon, but a little bit larger than horizon. So of course, include that you mentioned some. If they are spinning in the big fast enough, then they don't have to fall into the black hole, right? And or even escape to the infinity, right? So somehow the theorem says something else. I'm a little bit confused. So
Yeah.
Probably it's about the spherical object, not spinning, yeah?
That's right, that's right.
Oh,
This is, yeah, there's some, that's right, there's some implicit
I
assumptions
see,
here that,
without any angle on it.
that's right.
There is no appearance of angle.
Thank you. So this is where we want to bring in string theory. String theory offers us, some additional ingredients, extended objects. And one of the main nice features is that these extended objects can have this fractionation, have something called a fractionation effect, or they can fractionate. It's where the tension becomes fractional. And D-branes, for example, it sort of exhibit this feature. And so, and because they're fractionated, they can grow. They actually grow as G grows and as N grows. And so this actually allows you to be able to support something, because normally if you think about forming a black hole, you turn gravity on and the matter wants to collapse. But these objects tend to grow as you turn gravity on. And
What is it, N?
Oh, capital N, I think, is the number of brains that you're considering. Like if you have a stack of brains, yeah. And so, so this seems to be a way in which string theory would allow us to maybe support something that's horizon scale. And so how do you build such a configuration? Well, you take the objects that you have and you wrap them around the compact dimensions that you have. And a further hint that string theory might help us here is the work by Strominger and Vafa and Sen, and where they were able to count sort of the microstates of supersymmetric black holes in field theory. And so that sort of begs the question, or that would provoke the question of, what are these microstates that are counted in sort of a field theory way at zero coupling? How do you understand these things at strong gravitational coupling?
So I don't understand the brain tension proportional to 1/n, but you said the n is the number of brains. What is the meaning of that? Tension?
Right, so I guess the way I understood it is that, let's say I have n number of brains in my system, and then I want to take another brain and I want to add it to it. But when I do that, those existing brains are going to sort of have effect on this brain that I added, and it's going to cause it to fractionate. And so this sort of keeps happening, I think, or yeah. And so the fuzzball paradigm says that the traditional horizon is replaced by horizonless balanced states of stringy objects called fuzzballs, and they have the same mass, charge, and angular momentum and scale as the would-be black hole. And this addresses two main aspects: the storage of information and the release of information. Because you can think of the structure as sort of how the information is stored, and then how does that information, how is it released from the microstructure, and how is that different than, say, a black hole, like how a black hole would release it? I won't touch on this. Mainly, I will focus on the storage part, so the structure of the solutions today. But actually, there's many questions you could address as well.
So I'm just wondering how this is distinguished from, for example, the traditional Strominger-Vafa counting black hole microstate using Strominger-Vafa matched the black hole entropy of the D-brane bound state. They can't do it, and I'm wondering if that story is how this traditional story is distinguished from this point of view.
I think this point of view is attempting to build the microstates that they counted in field theory.
All right. Sorry. So, could you say that again? Sorry.
Yeah, at least the way that, so I understand the picture is that they have a count in field, say, some field theory technique. They're able to count, they find a number and it agrees with, the Bekenstein-Hawking entropy of the black hole.
Right.
But then I think now the question is, what are these microstates in the bulk? So this, we have an entropy, and
I think they did count the bound states in the string theory side, not the probability theory side. Because they,
that's right.
yeah, they thought about asymptotically flat black holes.
Mm.
They did not rely on any ADS-CFT, no CFT partition functionality theory argument. They just argued that the black holes originate from the D-brane setup, and then they count the bound states of the D-brane setup that match the black hole entropy.
Isn't it? Their counting is a flat space counting.
Yeah.
Flat background. There is some superpositionality argument there.
Yeah.
But here they want to really construct the curved geometry. Am I right? So they are not exclusive.
Right.
Or the number of grains, or the charge. If the charge is not that big, then I guess string counting, string theory counting is okay. But if number is very large, then the space-time, they will not allow the space-time flat, right? So then it should be something like the black hole, and maybe that's why you are saying some plausible paradigm or something. That's
That's
Open string counting is
so
the,
really two extreme.
that's right. One is that, oh, sorry,
I think the, compared to the Strominger-Baffa counting by using open string, here, quantum mechanically, that obvious. So, in my understanding, possible, but I don't know.
Yeah, so my question was like, is it something conceptually completely distinguished from this Schrödinger-Baffa type calculation or not? And this is also just the counting based on, so Schrödinger-Baffa philosophy is that they understood this black hole microstates arising from the bound states of the D-brane setup they constructed. So they use string theory to explain the entropy of black holes and provide the entropy in that way. So I'm just wondering if this possible. When I was a child, I thought this possible paradigm is completely distinguished from that paradigm. So now, but it seems like it's also using some extended object in string theory to account for the black hole microstate. So I just want to understand what is the distinguishing feature of this plausible paradigm from the Schrödinger question.
I think the distinguish, I think there's a connected, I would say, because normally in ADS-CFT, it's one-to-one. There's a one-to-one map between the states in the boundary and the states in the bulk. Typically, we think of it like that. And so the idea is, what's the one-to-one map of the states that you count in the field theory? What is the state, the geometry? So it's really resolving, it's really like a statistical view of the black hole. It's really saying, no, maybe I don't have a classical black hole. I maybe have an ensemble of these microstates that effectively look like a black hole, but there are some distinguishing features.
I see. So like you're not using this particular, like for example, D1D5 system, and then use that particular single system to account for black hole microstate, but you put extended object in randomly very complicated manner, and then that is.
Yeah, that's right. So you do use, the D1D5 is a big workhorse here, but you try to you have sort of additional degrees of freedom that try to sort of resolve the structure. Yeah.
Thanks.
No problem. Thank
You
you.
want to explain this object microstructure using just gravitational hair, right? Hair.
or you mean just in gravity?
Yeah.
Well, that's the goal, but okay,
Okay, not yet, okay.
yeah, that's the goal, yeah. So let me just briefly say a little bit about supergravity, and then we'll try to go into how the solutions are made. So supergravity is when supersymmetry becomes, you make supersymmetry local, and you can also think of it as the massless sector of string theory, and it should capture low energy collective effects. So microstate geometries are smooth horizonless solutions to supergravity, as maybe we were just discussing. And the way they're so in some ways it's kind of special sector, right? The way that at least that I have learned to sort of think about these is that they represent these types of states represent coherent excitations which back react to produce geometry, but similar to the way that a photon, sort of a collection of photons could produce a laser. And so it's a very sort of coherent, geometry comes about as sort of some very coherent quantum state.
Quantum state of gravitons or?
That's, yeah, so at least from the CFT perspective, you can construct, you can say I have some sort of say a quarter BPS states in this, or I have 1/8 BPS states, and the idea is that I turn on the coupling, and if it's sufficiently coherent, then I can interpret in the gravity, I can interpret it as like a microstate geometry. That's the idea. And so the two charge microstates, which sort of given the name supertubes, these two charge microstates, they do count the black hole entropy. They've been able to count it on the field theory and the bulk side. And the three charge geometry that I'm going to talk about today, they count some of the entropy. So this is a point of where people have differing views. Should actual smooth geometries be able to account for all the entropy? That's a debate, sort of a question up for debate amongst some of the sort of the experts. But anyway, this is sort of the idea of superstratas, that they're smooth solutions.
So in the parentheses small, in the that means a small charge.
Small black hole. Sorry, good question. Yeah, these two charged black holes, I think. Actually, I think the naive picture is that the horizon area is 0, but I think Ashok Sen, I think he computed he computed the corrections, and I think the black hole puffed up, but it's still really sort of small, sort of like a string, maybe string scale size, because you just have brains. When you put that third charge, that momentum wave, it acts as sort of a counter to the squeezing of the cycle, and so that's what gives you the big black hole. And then we would like to construct the states, the microstates. Yeah.
Why do you somehow pre-assume there will be no horizon in this case?
Okay, it's a conjecture. The conjecture is that everything is horizonless, that there's no horizon in phase space. Because that's a very good question. There's no proof, but in all the cases that have been seen so far, there seem to be no horizons. And if it appears like one may arise, it always seems like you can go to a different frame where you can sort of evade the formation of a horizon. So the logic is, if I have sufficiently many degrees of freedom, if I have enough, then I should be able to resolve singularities and horizons. If I can include enough degrees of freedom, okay, this is a conjecture. I understand it's just one framework, but that's kind of the conjecture, I think, is that.
And what astronomist observer is also horizonless, do you think?
Oh, like an observable?
Yeah.
Oh, what is an observable signature? That's tough. I mean, people are studying this. I don't have a lot to say about this area, but there are people, they're trying to sort of look at what are the signatures of this would be, of some sort of geometry or some sort of microstructure. Or you know, for example, we have a lot of data in LIGO now, and so is it that's a very good question. Is it possible to see this? So this is an active area. I think people, you know, what are the observable effects? But yeah, I don't have. I need to learn more about that aspect. But no, that's a very good question. What are the observable effects? There are some. There are some differences. For example, maybe some sort of tidal. If you consider tidal forces, because these solutions break spherical symmetry, it may have some more sort of complicated sort of moments because of the wiggles. This could leave an imprint on space-time, which is a little bit different than just the spherical symmetric black hole. But that's a very good question about what is the observable effects of this. So that's a conjecture that there are no horizons. It's not proven, but so far it seems none have shown up in the constructions that have, yeah. So here's just a picture of, just to have a picture. For example, the way you can do this is you take 2B string theory, for example, and you can use the 2B frame, you can use the 2A frame, but you have a manifold of 4,1. You can just think of this sort of non-compact space, and you have an S1 and you have a T4, and you can take this, take N1 D1 branes wrap around S1, take N5 D5s, wrap them around T4 across S1, and I have this common direction. And so the two charge states are counted by sort of the ground states in the CFT. And if I take the two charge states and I put a big momentum wave on it, these correspond to these superstrata geometries they look like the three charge black hole geometries up to a certain point, but instead of the throat region continuing on, it actually caps off. And so that's the distinguishing feature, is that somewhere far down the throat of the geometry, the microstructure is starting to be seen, and it sort of caps off right before it would form a horizon. So that's the idea. Yeah. So let's talk about superstrata and how do you build such solutions? And I apologize. I feel like I put too many equations in this section, so my apologies. I hope it can go smoothly. So first, since we consider the T4 to really sort of be roughly a spectator, you don't allow the fields to depend on the T4 direction. And so this allows us to use 6D supergravity to try to understand these solutions. They're supersymmetric. And so this sort of tells you that they're time independent. And so there's a general form that has been worked out for sort of this particular supergravity. So we use 6D supergravities, minimal gauged. And it consists of various degrees of freedom. So we have the metric, and this X stands for different fields, tensors, vectors, and you have you have this dilaton factor here. And so this sort of this metric ansatz was worked out based on this amount of supersymmetry, that you have a base space, it's 4-dimensional, and then you have your one direction, which you consider sort of to be the common direction. So even though this is in 6D, we remember that this is actually, we're trying to understand physics in 10D. And so you can combine the Y direction and the time direction into these null coordinates here. And roughly your U coordinate represents roughly the time coordinate. The V coordinate represents sort of the spatial coordinate, but in this null coordinate system.
So Y is compact S1?
Yes, that's right. That's right. Y is compact.
So 60 is essentially the world volume of D5 or?
So with the D5 wraps the S1 and the T4, but because we're allowing the theory not to depend on the T4 directions.
The remaining.
That's right, exactly. So you obtain a system of BPS equations. Because this is a supersymmetric theory, you get BPS equations. And the way this typically works out is that you can recast these differential equations on this base space that I showed, this 4D base. And what was found, actually, the main reason that this could probably be solved is that the BPS equations were found to be linear. And so when something is linear, it's much easier to solve. When I say easier, not easy at all, but easier than, say, a nonlinear system. And the BPS equations organize as in terms of layers. And this is where the word strata comes from, because strata is like, you could think of the rock, different layers of rock, or like a tree has different layers, meaning that you solve them in order. One layer feeds into the next, that layer feeds into the next. And you're able to sort of solve for all the fields this way. So that's the way they were, the procedure. And so, as I was saying, this is the general flow. Remember this base space I showed? You solve for this guy. That feeds into solving for the fluxes of your theory. The fluxes then feed into solving the back reaction of the metric, which contains the momentum and angular momentum. And so a natural sort of starting place for the 3-charge solutions is the 2-charge solution. So a very simple 2-charge solution, and you put the momentum wave on it. So that's the logic. You start with a simple 2-charge state, one that you can solve, and you put the momentum on that, you back react it, and that helps you get the 3-charge geometry. We start with a 0th layer, and this was worked out. These equations just indicate that it has this particular structure called almost hyperkähler. I still need to learn more about the intricacies of this, but in short, I think it has 3 anti-self-dual forms. And in the previous slide, there was this beta, which appeared as sort of this vibration. I can simplify my life considerably if I consider this fiber to be independent of the compact direction, or the null, or the v direction, which is t plus y. And so this choice essentially allows the remaining BPS equations to be Laplace equations. So we see here the fluxes don't enter. Into this 0th layer. So it really amounts to solving for beta, because we're going to take these forms here. We're going to take this here to be 0, and so the only thing that's really going to show up is beta. And as we go through the layers. So and the physical interpretation that this beta will carry, I think is a KK monopole when you consider in the full 10D framework, because you can uplift this. So I'm in 6D, but you can uplift back and you can have the interpretation of all these fields in terms of the branes.
Oh, sorry, so you're working for now in 6D supergravity.
That's right.
And you're starting base geometries almost hyperkähler, so you have JA, BC.
That's right.
Then so you're saying these equations are, once you find a solution to that, you get the BPS solution in 6D supergravity without flux for now, and then
Right.
Start this go beyond the 0th layer to find the solution with flux. So
that's right. Well, so this is part of the story. This is part. You solve for the sort of the base. This sort of allows you to have the base part down. Then I need to solve for the flood. That's right. I need to solve for, so the base is just part of the geometry, but then the other part of the 6D geometry has these fibers and this omega. So this omega is roughly kind of like an angular momentum you can think of. And I need to,
나중에 metric untouchable hyperkähler structure here.
as far as I know, I think
That is,
that guy, yeah, this is the base, this guy here. But we're gonna actually take this to be R4. So, I mean, you have to kind of pick the simplest, you pick where you can sort of solve the problem. And so we end up taking this to be R4, but you can write this in sort of an interesting way so that you can see that that you have the two charge solution first, and then you put the momentum wave on it.
That 4 dimension is the T4 or?
So this 4 dimension is your sort of non-compact space. So the T4 is right now is not in the game, right? It's
Non-contact duration in the 6 dimension.
yeah, that's right, that's right.
It shouldn't Euclidean hyperkähler.
Euclidean. I thought it would be Lorentzian, but I'm not.
I think so because you used T, the first part, right? T coordinate, I guess that's the.
That's right.
That's Euclidean. Then your hyperkähler is in about T4 or no?
I think, as far as I understand, the base, this base geometry, according to their analysis, it seems like the base is what's hyperkähler, almost hyperkähler. Yeah.
So where is the circle direction in that matrix?
The circle direction is great. It's encoded in this V. That's right.
It's Y.
Yeah, that's right. So that's right. T minus Y, T plus Y. That's right.
And dilaton is trivial at the zeroth layer.
Not trivial because zeroth layer, we don't say anything about the dilaton yet. The dilaton hasn't come in yet.
Okay.
It will come in.
Are you in string frame or Einstein frame?
I think this is an Einstein frame. I think. Yeah, I think this is an Einstein frame. So the first superstrata, which I'm not reviewing in detail today because I wanted to talk a little about some of the work that we did recently. But so this X that I showed you, which gives you your extra matter, they considered two tensor multiplets. And so the bosonic content of the theory was this here. And so those solutions, in essentially, you have a zeroth layer, you have a first layer, and you have a second layer. And it's the second layer where you're able to solve the momentum and angular momentum. In this talk, I will present some of the recent work where we consider not two tensors, but a tensor and a vector multiplet. So, and this gives you some sort of different solutions. And so this is just how we kind of decompose the tensor field and the vector field. You can write it as, you can sort of pull off the fiber part, and you have a base part. And the same thing you can do with B, but this is a two form. And so I can have sort of both of the fibers, and I have a scalar function. I can have one of the fibers, and I have this is a one form, and then I have no fibers, and so this gamma is completely has legs on the base space. So this is just sort of a way to decompose your fields. And we choose to work in gauge invariant quantities, so you can take these fields and you can compute the field strings, basically. And so that's just what we're doing here. We're going to utilize the field strings, and you can dualize. So I have G here. It's a three form. I can dualize this, and then I can sort of introduce a B tilde. And so it also has accompanying with it, it has some, so your fibers here, and you have a scalar, then you have a one form, and you have a gamma. And so using this here, we're able to write these quantities in the same way that we wrote the fields. We're able to sort of divide out the fibers and the base contributions. And so that's just what this is saying here. Is a way to split up your contributions. And so in the previous equation, these thetas showed up, and this is part of what we solve for, is these thetas. So there's a lot of simplifications that we make to make it actually tractable to solve. Typically, we take the majority of the quantities like this that are derivatives with respect to v, we take to be zero. I think maybe people, I was talking to my colleague, and they tried to do maybe more complicated setups, but it's just even more complex to solve the equations. So, but in general, yeah. And so you have the gauge invariant quantity. So we've described the sort of the fields that we want to try to solve for. Now I want to try to motivate this from the field theory perspective, because there is a dual field theory interpretation, and that is the D1, D5.
So the previous one, since I'm afraid I couldn't follow the detail, but the punchline is that the gammas and the A's and the beta and the Z and the A tilde, those are essentially independent functions that describe the degree of freedom of the system.
That's right.
Metric.
Yes.
Can I understand that?
That's right. That's
And
right.
at the end, you will have a 3 parameter family of solution.
Actually, I think these are, you mean in terms of the variables?
3 parameters.
You said 3 parameters.
3. You said 3. Strata, superstrata. This is superstrata.
Oh, you mean like, yes, like charges, I think. Yes, you have the Q1 charge. That's right. You have the Q5 charge, and you have the momentum
So
charge.
at the end of this all steps, we will end up with the 3 parameters.
I think in that, I think, but there's some relation, because you also want it to be smooth. Yeah, there's some regularity conditions that you have, which relates the parameters of the theory, but yes, I'm just yeah. You definitely have the three charge. You have the D1, essentially the D1 charge or the F1 charge. You have the NS5 charge or the D5 charge, and then you have the momentum. But yeah, maybe when we get to that, I'll be able to explain a little bit better. So I wanted to motivate the states that we were interested in from the D1, D5 system. So the D1, D5 CFT is 1 + 1 dimensional CFT. And essentially, you look at D1s and D5s wrapping S1 and T4, but you take a low and G limit, and you consider the field theory on this system. And it's an orbifold field theory, which means that you have sectors that are twisted or untwisted. And it has superconformal symmetry. We have 4 generators on the left and 4 on the right. And so we have these Virasoro generators, we have the superchargers, and we have the current operator. These are SU2 current generators. And so the dual of the starting point is something which we call this maximally spinning supertube. It is a 2-charge state, and it does have a CFT interpretation. And ultimately, we're going to end up in the Ramon sector. And so this 2-charge state carries these charges here, and we can make 3-charge states by taking combinations of combinations of the generators. We can make 3-charge states. And what we're interested in, because we have a vector, we need to make a vector in the CFT. The way we make a vector is we leave. So this A and these A dot indices, they are T4 indices. They carry T4 charge. But remember, this is just from this viewpoint, it's just a charge. but there is, in the 10D theory, we do have a T4, but now it just manifests as, we have, it carries a charge under this direction. So this is a SU2 charge. This A dot is a SU2 charge. When you can combine this, SU2 cross SU2 is like an SO4. And this is where these states become vectors. So I have an A and an A dot, an A and an A dot. And so these two states differ by these R charges here and these R charges here. And so what we attempt to do is to construct the gravity dual of these three charge states in the CFT. So I just wanted to motivate from the CFT the states that we try to compute in gravity.
I thought your supergravity tended background has trivial T4 sector. There is nothing there.
Oh, so when I say trivial, I mean it doesn't depend on the directions of the T.
You still have
But it can have like you can think of it as having legs on the T4 or polarizations. Yeah, that's right. Okay, so the starting point is the round super tube. And basically, as I was saying previously, we take this base geometry to be R4 actually, because this can be solved. But you can rewrite R4 in an interesting way, some sort of spheroidal coordinate system. And this sort of makes manifest this sort of maximally spinning super tube geometry. And so if you take these values, if you take these quantities here, and you put them into that metric that I showed, you get a two-charge state called the maximally spinning super tube. And so everything else vanishes, except you have your sort of harmonic functions. This beta, which I was mentioning, sort of represents a monopole. This omega represents your angular momentum. And this gamma 1 and 2 is part of the fluxes that you have. And so this sigma is R squared plus A squared times cosine squared. A squared tells you about the size of the geometry of this super tube in space-time. So this is the starting point for so we sort of build the three-charge solution on top of this. But to do that, we want to take this and we want to perform a coordinate transformation like this, because what this does is after all the dust settles, this super tube solution actually takes this form, which is global ADS3 cross S3. And so we'll take this to be the starting point to construct our geometries. And this coordinate transformation that I did is equivalent to what's called a spectral flow. So in string theory in the CFT, or in string theory, or in the CFT, you have NS sector states, you have Ramon sector states, and you can go between them. And the manifestation of that in the supergravity or in the gravity dual is this sort of coordinate transformation on the angles. So we want to construct first the perturbation that corresponds to this vector that I was showing. We want to turn it on. So we make an ansatz. But because we have a nice symmetry in our geometry, we can make this informed ansatz here, where we sort of split off the sort of S3 dependence, which depends on theta, and the R dependence. And just as in the CFT, my gravity theory has these symmetries. ADS3 cross S3 has these isometries. And so you can write down, I didn't write the form, but you can write down the gravitational versions of this commutator algebra. You know, it has partial derivatives and things like that obey. So these are the global generators of the Virasoro algebra. And also we have the sort of the SU2 factors here. So I didn't write them, but you can write these in terms of gravitational. Yeah.
So you are trying to add a momenta, right?
That's right.
For the three charts.
That's right.
That momenta is along the S1, right?
That's right.
That's shared by D1 and D5.
That's right. That's right.
So which coordinate is that S1 coordinate?
So that S, okay, so it turns out that
Essentially Y coordinate.
it's essentially the Y coordinate.
Okay.
That's right, but we
And
will,
then
yeah.
angular momenta is rotation on which space?
Right, so you have phi and you have these angular directions of the S3. That's right. That's right. And you also have theta as well, and then this is the R direction. Yeah. So I have a CFT state, and it should obey some relations when I act with the Virasoro generators. So I can take the same, those generators expressed in gravity, and I can act on this ansatz that I made here, this ansatz. And that can give me what the state should be. You essentially get some equation, you solve this for these charges, and you obtain what the perturbation is, what the starting one is. And so that perturbation for this plus state, this is the lowest descendant here, is given by this. I can act with L minus ones on this and J zeros on this guy, and it can give me the perturbation for general K, M, and N. So this should be K, M, and N here. So this is in the NS sector, and then I can make a coordinate transformation to the R sector. The point here is just that you can build the perturbation with the Virasoro generators in the supergravity theory. You find the perturbation of the lowest descendant, and then you can act on that with more L minus ones, more J's, and you can build up your energy, you can build up your angular momentum.
Question. So basically, I guess your goal is just to find the background corresponding to each microstate, right?
That's right.
And so in this way, you are creating state characterized by the same three charge by using this vector perturbation. So you're generating you're generating geometry associated with each microstate, right?
Each K, M, and N, yeah, will have some sort of.
Okay, but so I thought, for example, going back to Schrödinger buffer, they computed the number of microstates associated with three charges. For given three charges, there are multiple microstates. And then what I expect is, so same three charges, there are multiple states.
That's right. That's right.
So your microstate should have same three charges, but they have to be distinguished if you want to generate geometry for each state, right? So,
I think that ends up being the case because.
So this kind of vector perturbation does not change the three charges.
I think there might be a relation in which there is a relation amongst the charges. And I think it's possible that that relation is satisfied for different choices as long as, so I'm not recalling the exact relation, but I think there is a relation in which you can sort of pick different charges as long as they're constrained, the values are constrained. I think that's the case, yeah. So here's just, if you go through that, you can construct the other vector perturbation. So we have two different ones, and they give two different vector perturbations. This is the second one, and these v hats and these deltas are just given here. So so you see the dependence on v, you see the dependence on phi, psi, r, and theta. So these solutions really are if you take all the fluxes and the geometry, they're functions of 5 variables.
Could you remind me what was the quantum number K, M, and N?
Yes.
N? They are, along some.
So K from the CFT perspective is sort of the winding of your, you have some primary state that you start with and you build on top of that. And this K is that winding. The N is sort of the energy and 80, I think it's like represents sort of the momentum along the Y circle momentum.
So
And
S1,
this M is sort of your quantum number in the S3.
S,
The angular directions of your sphere. Yeah, that's right.
And these are three charges, wait, 1 to 1.
We're getting, that's right. We're
You have
getting,
degeneracy for given Km.
these are 3 charged, right? Because we have this N here. This is what gives you sort of the momentum. Okay, there's also some coming from the J plus, but yes, this N sort of characterizes this momentum wave.
And
So
the degeneracy, I think that was look at. So.
Yeah, I think there is a degeneracy. There's some relations that you obtain. I'm not recalling the exact relations right now, but I think there are relations that you obtain where you can choose maybe different quantum numbers for the same sort of overall momentum, let's say, or the same overall charge of the
Well,
system.
at this level, if I fix Kmn, there is only one state.
That's right. At this level, I haven't imposed any sort of regularity. So we haven't finished. We have to go to solve all the way through, and regularity imposes some conditions on the charges. But at the moment, we haven't solved everything. So at the moment, I just have K. I have a perturbation. I have K, M, and N, but I haven't solved the full system yet. Yeah. So, I should be finishing. Okay. You have the first layer. Maybe I'll just go quickly. You have layer 1, which combines Z2 and theta 1. This corresponds to roughly, you can think of this as the NS5 ring. It's the heaviest object. It's unchanged by the presence of the vector fields, and it only involves the tensors. And so actually the 2-charge solution continues to be a solution here. And so the second layer is when you solve for the vector field. And so in comes the vector fields. This is the second layer, just to state it. So now you're starting to see the sort of strata structure, because from the first layer, I get Z2 and theta 1, and they enter as sources in the second layer. Let's go quickly. So just reminding these perturbations here, these are the perturbations. Now you get to the third layer, you solve those, you get to the third layer, they enter as perturbation, they enter as sources in the third layer. And this solves for the pair Z1 and theta 2, which is interpreted as F1 strings. These are the lightest objects. And so basically the NS5 affects the vectors, and the vectors affect the F1 string. So you start to see sort of this layer structure. And I'll just go quickly. And then my apologies. There's a fourth layer where you actually solve for the back reaction of the momentum, the angular momentum, and this sort of represents your linear momentum. Okay. So the summary of what we did is we started with a vector perturbation. We used the knowledge of the CFT to build it. We started with an ansatz. We solved the BPS equations. Layer 0, layer 1, layer 2, layer 3, and layer 4. And I'm flashing this up because you can just to say that there are solutions. You can derive solutions for the 2 different perturbations that we started with. And I should say that this layer here is the full back reaction, because this comes in at order B squared. And so this is no longer a perturbation, but this is the full back reaction of the system at this point, is the third layer, because now you're solving for the momentum and the angular momentum, which goes into the metric. And you can, so this is you can analyze these solutions, you can extract the angular momentum, you can extract the circle momentum. So maybe this might answer the question of degeneracy. So as long as I fix QP, I can play with these guys for the same QP. I think this might be towards your question about degeneracy. So I fix this guy and I can solve sort of different versions of these that satisfy this.
And if you count that the number of possibilities, does that account for the entropy?
Very good question. We didn't do that for this. We didn't do that for this analysis. I don't expect it to be different than what was done for the previous. So for the first superstrata that were built, they did do the counting. And the counting goes like, the counting goes like, like this here. So I have N1, N5, and I have NP, but under the square root, I also have a half. I don't expect that this will enhance. So our expectation is that this doesn't solve this part. This doesn't give you the full guide. But it contributes probably in this order, but we didn't do the counting, but that's a very good question. Yeah. Okay. You can see the D1D5P black hole by taking the simplest sort of ansatz with everything else 0. And so this is going to give you the D1D5P black hole. This has an infinitely long Froh region. And so we plotted out, so our solutions has ADS3. So this is the Y circle, ADS3. But then there's a long region where you do have the ADS2 cross S1. So in this region, it sort of mimics the 3-charge black hole. But then as you go further into the geometry, it begins to cap off. The Y circle starts to shrink. And so this is where it starts to differ from the 3-charge black hole.
What is A? A is the size of those ones?
So A is the size of, so we have this, our bottom component, our sort of base structure is this 2-charge state. And so A is the size of this.
Size of the
A is the size of the 2-charge supertube in the non-compact space. It's like a sort of a circle, I think like a ring. So the A is the size of the object that's supporting. So the momentum wave is along the compact direction, but it's also oscillating the system outside of the compact direction and also in the non-compact directions.
Is A given by Q1 and Q5 or?
Let me see, did I write the relation? There is a relation, but here. So so if you impose regularity conditions, it's smoothness. So this is where the smoothness, so you impose smoothness, that the geometry is completely smooth. You get a relation between the charges, the A's, and this B. Yeah. So this is where, so without smoothness, you would get some sort of singular behavior. But you impose smoothness and you obtain, the charges have to be locked together in this way. Okay, my apologies for going slightly over time. And so the conclusion is I try to motivate some of this, why we need black hole microstructure. How do you compute the solutions? And we looked at smooth 3-charge geometries. We try to look at the 3 microstates of the 3-charge black hole. It's subleading in the entropy by, so these are probably just as subleading as the original ones that were built. And so we analyzed the charges and we looked at some of the behavior. The nice thing about these solutions is that you can dualize into a frame where this is all completely in the NS sector. And so one of the future directions is that we want to try to understand string world sheet. If we can understand these geometries from the string world sheet. And then the string world sheet can take you further than supergravity because it is you have more sort of information, like string theory can sort of give you more resolving power, basically, than supergravity can. So that's all I have. My apologies for maybe not being so clear on some of the aspects, and I think it was too many equations, my apologies, but this was the first time I talked about this particular aspect of the geometry, so thank you for listening.
Yes.
Okay, so your solution is essentially three parameter solution K and M and N. So are those three parameters related to, let's say, if we think about Rn ADS black hole, Rn, yes, then the mass, angular momentum, and the rotation. So those three charge usual black holes charges. Are those related by some coordinate transformation?
Let me see, I think the charges, so the momentum charge, so this is the momentum charge, and you see we have, it's a function of M and N and K. I can play around with these numbers such that I keep this fixed. So that's gonna give some sort of, I can choose different values. I think it's similar to the question he was asking about the counting. And then I have this regularity condition also that I have to obey. I suppose you could substitute this guy into this guy and play, and so this is the other two charges of the three charge black hole, Q1, Q5. It's related in this way to the parameters that were of the solutions, and this momentum charge is also related. But I must say I didn't try to count the degeneracy of this. I didn't look at that. I didn't consider that.
You will.
I guess the question is, it's probably not gonna, I mean, we should do it probably. We should probably do it, but it doesn't seem like it will be any different than what the other guy, what was shown before. But yeah, we should do it. We should do it. No, it's a good question. Like, can you, because they do have, there's a few papers where they do count the degeneracy of the superstrata. Like they do some sort of counting, and I'm not so familiar with the techniques at the moment. But yes, we should, yeah, that would be something to do, would be to count these and see. It seems like if you want to get the leading order entropy, remember I said that, so we have this T4, but nothing depends on the T4, none of their coordinates. But it seems like if you want to get the leading order entropy, so if you want to account for the full entropy, maybe you need a T3 and you need to take another direction of the T4 and sort of bring it into the game. So then I have the Y direction. I have, say, X1 is one of the T4 directions. Yeah, and then I have the non-compact space. Now to build these, to try to build these is even more complicated because now you essentially need 70 supergravity. And it looks like they may come from some sort of brain webs in the compact. Like then you may need to go to M theory. There is some work in this area, but to bring in this extra direction and cause the fields to depend on it will be, I would say, even more complicated. But maybe the thing to do would be to try to use the world sheet, string world sheet. That's what my colleague and I, we've been talking about recently. And so what these geometries do is you can dualize this into a frame, because you can go to an NS frame where all the fields are NS fields, and you can try to understand it from the world sheet. From that analysis, maybe you can see how to include this extra direction in the, okay, this is all this words right now, but yeah. So the current status is people are trying to build sort of the leading order, the contributions that are leading order in the entropy.